Consider the function f of x equal to 2x to the fifth plus x cubed plus 5x minus 6. Show that this has exactly one root. You're probably thinking that this problem looks very much like some of the problems we've solved before when discussing the intermediate value theorem. I'm going to point out later that this is not exactly the same. One of the things that you might remember us doing is trying to find two specific values where f becomes positive and negative. F of 0 is negative 6. The calculation, f of 1 equals 2. So you have a negative number and a positive number. So between negative 6 and 2, the number 0 is an intermediate value. And because f is continuous on 0, 1, there is some number between 0 and 1. Here I've denoted by q, such that f of q is equal to 0. But see here, the conclusion is the following. F has at least one root. But that is not what this problem is asking us to do. It's asking us to show that there is exactly one root. So right now, we have opened the door to there being one root, or two roots, or three roots, or four roots, or five roots, but we got to show that actually you can't have two roots nor three roots. You can only have one root. Nothing fewer than that, and nothing more than that. Now what we're going to do is show that we cannot have more than one root. So the proof technique we're going to employ here is to prove by contradiction. Let us assume now the opposite of that and show that by assuming the negation of what we're gunning for, then something wrong in the universe is going to happen. So in case some of you have forgotten how to prove by contradiction, it's like you're in a court, you're trying to test somebody whether he or she is telling the truth, and then that person says, oh, I was at this place at this time. And then you make a counter argument that, oh, but if that was true, then this impossible scenario would have happened. Therefore, you must be lying. Therefore, what you're saying couldn't be true. So what we're doing is something similar. So suppose the function f has two roots. Okay, just so it's clear, I'm not saying f has exactly two roots. Okay, there could be three or there could be four, but if there were three roots, choose any two of them. If there were four roots, you could always choose two of them out of the four roots. So suppose f has two roots. Let's call them r and s. So they're different, so r is less than s, and because they're roots, f of r equals f of s. Now, in what way is this going to be useful? This is going to be useful because at this point, we already have the conditions of Rolle's theorem. F is a polynomial, so it's continuous and differentiable everywhere. So therefore, it's continuous on Rs, differentiable on Rs, and because f of r and f of s have the same value 0, therefore f of r is equal to f of s, which means that we can conclude the conclusion of Rolle's theorem. There is some number c between r and s such that f prime of c is equal to 0. Alright. Well, we're trying to prove by contradiction, so we have to find something wrong that's going to happen inconsistent with reality. F prime of c is equal to 0. How does f prime the derivative look like anyway? From an easy differentiation of this polynomial, you get 10x to the fourth plus 3x squared plus 5. Alright, we just claimed the existence of a critical number of the first type, c. F prime of c is 0, and this is the derivative. Therefore, 10c to the fourth plus 3c squared plus 5 is equal to 0. Do you see any alarms yet? Any sign that something is wrong, something is not right? look at the left side, 10c to the fourth plus 3c squared. You're adding two terms which are non-negative, so that's at least 0. And then if you add 5, that's going to make the left side, in fact, at least 5. And so therefore, the left side is strictly greater than 0. So how can this be equal to 0 when the left side has to be strictly positive? It can't. It's impossible. Therein lies our contradiction. So therefore, by assuming you could actually find these two different numbers, r and s, different for us to be able to form an interval rs, which allowed us to eventually conclude something from Rolle's theorem, then you get this impossible situation. So therefore, the assumption, the premise that f has two roots is false. So therefore, f cannot have two roots. So therefore, you can't have three roots, because if you have three roots, you could sample two out of them. And if there are four roots, you could always sample two out of them. So that has now closed the door on the presence of two roots, three roots, four roots, and so on. All right, f is at most one root. But now if you take those two conclusions in blue simultaneously, there's at least one root, and yet there is at most one root. So meaning you can't go lower than 1 for the number of roots, and you can't go higher than 1 for the number of roots. There's only one conclusion. F has exactly one root, and that's what we're trying to do. Jaron. Okay. Let's solve a similar example. Show that x to the fifth plus 2x cubed minus 6 equal to 0 has exactly one root. But we still have the solution of the previous example to serve as a template, so the solution is going to be broken down into two parts. First, we show that f has at least one root, and then the second part show that f has at most one root. And to show that f has at least one root, let's use the intermediate value theorem. And to show that f has at most one root, let us use Rolle's theorem. Okay, part 1. First, we gotta give a name to the function we're gonna work with. You're gonna use the IVT or RT, Rolle's theorem. You gotta have a function. Let's just give this a name. Let f of x be x to the fifth plus 2x cubed minus 6. And then find two numbers on which to evaluate f at, where the outputs are positive or negative. F of 0 is negative 6. F of 1 is just going to be negative 3, still negative. But f of 2 is 42, you can check, which is positive. And then just to ensure that we have all the conditions satisfied for the intermediate value theorem, all right, f is continuous from 0 to, in fact, it's continuous everywhere because it's a polynomial. So therefore, by the intermediate value or intermediate zero theorem, there's some root between 0 and 2. So there's some number r such that f of r is equal to 0. All right, I have the option, the prerogative to choose the variable. Like earlier, I think I used q for the root, but here I'm using r. You could use n or some other letter. Okay, f has at least one root. Now, let's use Rolle's theorem to prove that f has no more than one root. We want to show f has at most one root. Oh, by the way, when I say root, I'm referring to a real root. It just occurred to me, some of you are probably thinking, wait, this is a fifth degree polynomial. Aren't there supposed to be exactly 5 roots? Well, if you're going to include complex imaginary roots, it's going to be exactly 5. But here in this course, we're dealing with everything real, all real numbers, so real roots, that's what we're talking about. Okay, now let's go prove that f has at most one root. By contradiction, suppose we can find two of them. Let's call them a and b, a less than b, so they're different, and then f of a and f of b are both 0. All the conditions of Rolle's theorem are satisfied. F is continuous in AB, differentiable in AB, because f is polynomial. And then f of A equals f of B, right, because the common value is 0. So therefore, RT conclusion, there's some number C between A and B, such that f prime of C is equal to 0. But what's f prime? It's 5x to the fourth plus 6x squared. And therefore, 5c to the fourth plus 6c squared is equal to 0. Earlier, we got a contradiction here because the expression on the left side is strictly positive, so it cannot be 0. But if you look at 5c to the fourth plus 6c squared equals 0, is that really such an impossible situation right now? I mean, you're probably thinking, this cannot be negative. But see, that's the best way to describe this expression. It is non-negative. It is not negative. So it could be positive, but hey, you know what? It could be 0. So right now we don't have a contradiction yet. I mean, problems come in different forms, shapes, and sizes. So let's try to explore further. Alright, just because there's nothing more we could do, factor out c squared, so you have 5c squared plus 6, and that's equal to 0. Well, if you're looking at 5c squared plus 6, this expression is strictly positive because it is at least 6, alright? And so if you have this product which is 0, and the second factor cannot be 0, then it must be the first factor which is 0. So in other words, c is 0. But yikes, we don't have a contradiction yet. Well, there's going to be a contradiction here, alright? Well, okay, the C that the RT proposed is 0, and it's inside this interval. Well, I guess that forces A to be negative and B to be positive. But I'll just go ahead and take the conclusion that is going to be useful eventually, because I've solved problems like this before. A is negative. Well, what would then be such a bad thing about that? F of A is 0, remember? That's the only thing that justifies the presence of A here. A is 0 when plugged into F. But if you actually do the plugging in, you're going to have A to the 5th plus 2A cubed minus 6. Now, if A is negative, A to the 5th is negative. So is 2A cubed. And then minus 6, of course, is negative. So here you have three terms. Adding them together would give you a negative number. Do you now see the contradiction? F of A is supposed to be 0. And yet here, F of A is negative. Contradiction. So therefore, we try to contradiction. F having 2 roots is impossible. Therefore, F has at most 1 root, and F is exactly 1 root, therefore. Alright, almost done here with Rolle's theorem. Okay, example, please try at home. Show that 3x plus 2 cosine x plus 5 has exactly 1 root. You could try that on your own. The function you end up getting here is not polynomial because of cosine x, but you know, it's still continuous and differentiable everywhere. So try this on your own. Then one more example. Show that x to the 4th plus 4x plus c has at most 2 roots. Alright, so I'm not asking you to show that it has exactly 2 roots. So you have to show it has at most 2 roots. Now the conclusion of the IVT is towards showing a function has at least a certain number of roots. But here we're only supposed to show that f has at most a certain number of roots. So it's the second part that you have to be able to do for this function. So it's Rolle's theorem that you have to use. And just to get you started, it's also going to be by contradiction. So you have to negate what's being asked of you to prove. So you want to show that there are at most 2 roots. That means it's impossible to have 3 roots. It's impossible to have 4 roots. All right? So therefore, suppose you can find 3 roots, R, S, and T, which are different. And then try to explore on your own. If you're unsure how to proceed or you get stuck, feel free to ask. Thank you. And of Rolle's theorem, I realize I haven't really talked yet about the mean value theorem. That's going to be the next video. Bye-bye.